So I have to say, chapter 13 is probably my least favorite chapter of all of Biochemistry 2, but it's a necessary evil. So, but we'll go through it pretty quick. And most of it, or a lot of it, especially this first part, is really a review from like Gen Chem 2 in bioenergetics and thermodynamics. And it did literally drive Boltzmann crazy. Does anyone know? I know people in entomology talk about Boltzmann, but you know, guys, who is Boltzmann? What is he known for? Instead of being crazy, he committed suicide. It's like Debbie Downer.
Is there a particle named after him?
There's what?
A particle named after him?
Possibly. There's a constant named after him, Boltzmann constant. But he is really the one that helped do the second law of thermodynamics, and is the one that categorized and started discussing entropy. And the second law of thermodynamics, if you think back to physics and Gen Chem and stuff, is the fact that the entropy of the university, it's true as well. The entropy of the universe is constantly increasing. Okay, and so, and what was entropy in general? What is it a measurement of? Disorder, randomness. Did you say it's takedown? What?
I said breakdown.
Oh, yes, it can be breakdown and all that kind of stuff, yes. Okay, but, yeah, no, he did. He's the one that came up with the equation, what, S is equal to K, natural log of W, and that little K is named after him, Boltzmann constant, which is also pops up in other things, too. Okay. But no, he was nuts, and so whenever he died, his request was that on his tombstone to have that his equation put on there, and lo and behold, they've got a big monument kind of thing to him in Vienna that it does. It says Ludwig Boltzmann, and it's got S is equal to K, natural log of W. So that's what he wanted to have put on his tombstone. So okay, so in this chapter, we're gonna go back over the laws of thermodynamics. Relationship between energy, entropy, K, and Q. We'll go a little bit, well, just a brief review of the types of biochemical reactions of cells, the importance of ATP in vivo, that one I may go really quickly in because we're going to see it over and over again, and then the importance of redox reactions in vivo as well. Okay. So the first thing up, and this PowerPoint's not available yet because I shouldn't get to load up. But I did put the suggested problems for chapter 13. That's available. Okay, what does the term bioenergetics mean? And since this was, that gave you the answer. It's a quantitative study of energy transductions. Okay. We already went over what a transduction was last chapter of sorts, where we're just changing from one form of energy to another. Ooh, right. And so this was the first law of thermodynamics, from example of the first law of thermodynamics. I'll give you a chance to read it. So what is the first law of thermodynamics?
Energy can never create nor destroy.
What?
Energy can never create.
Yes, it's never create nor destroy energy. Okay, it just changes from one form to another. Right, so there's technically what it is. Okay. Then we have the second law of thermodynamics. This one I do like. I actually like looking. Okay. So what it states is that for all natural processes, the entropy of the universe is increasing. And does anyone remember from chemistry or physics, like what do they mean by universe? Like what's the definition of the universe? It's composed of two things. What? What is the definition of the universe? Those are two things, in chemistry and physics. I assume they cover physics as well, but I know in Gen Chem too, we always learn about it. No. What? I think you're on it. What were you going through in your muddled state, as you'd say?
Is it that's what's inside the area, I guess, and then the area itself?
Okay, yes, it's the right idea. Mm-hmm.
It's like
They had terms for the area and the area around it and all that kind of stuff. The system?
yeah.
What's the area around the system? What?
I don't know.
I thought you said it though.
Did I say it? I said circumference.
Oh no. No. Said it like it. There's the system and the what do you call it? Surroundings. See, I thought you said surroundings. So there's the system plus the surroundings. Okay. Circumference. So another thing to think about is how do, apparently at least, how do living organisms violate this law by their sheer existence? There's some people even use this as, like the philosophical or almost a theological debate. So how do living organisms, or not, how do they apparently violate it, and how don't they violate this?
How do they violate it?
Yeah, I mean, how does it look like they violate it?
Sickness, for example?
Sickness?
Am I thinking of it wrong?
I think so. So, because what was entropy?
The disorder.
Randomness and disorder.
Yeah.
By being alive and actually functioning, you would think that would
Like growing up.
What?
Growing up.
Growing up?
Growing up.
Okay, growing
As
up.
you get older, you appear to be more like complex. You start as a baby, like.
Right, there's complexity. What about even on the more, and that's a good one. I haven't even thought that one yet. What about on an even more simplistic scale? Cellularly. Like, how does the cell apparently violate the second order?
make you think so.
What's what? Is it disordered or ordered?
It's very ordered.
It's very ordered, and so there are people, they even talk about this, how does it, like, what about proteins just folding in general? If you are a true, sheer, strict definition of entropist, then, proteins would never fold, right? Because just by the very nature of folding, it's going to be becoming less entropically favorable and so on and so forth. So the question is then how, this is an inherent violation. Okay. So this is at least how even like evolutionists and stuff would explain it. Okay, is that unlike that chemistry experiment where you have a closed system, a living organism is open. Okay, so there's a transition that's occurring between that system and its surroundings. And that's how the cell can maintain its internal order. Now cells are isothermal, which what's its isothermal mean? What? Iso? Same? Same temperature, same heat. What does that mean? If you got this little cell, this is not on the scale. What is the temperature of that cell? It's the same throughout, okay? And then isobaric.
The same pressure.
Same pressure, okay. And so they require sources of free energy. Okay. And by the way, the way that some people argue for protein folding, it's not in this next one. The way that some people argue like protein folding and how the protein folding isn't a violation of entropy, for example, is that they say that, does anyone want to take it rather than me giving away the answer? Like, how can someone, let's say someone who's completely an atheist, how would they explain that this is not, protein folding is not necessarily an apparent violation of the second law of thermodynamics?
Isn't energy still being utilized to push against that?
Perhaps what energy? So what is?
Hydrophilic reaction.
Okay, it has to do with hydrophobicity, because what they say, this is what they say, take it for whatever it is if you imagine, you know, we have our little ribosome, so I'm going to name Frosty, and then you've got this nascent protein chain coming off. Of course, there are going to be patches of it that are hydrophobic and patches that are hydrophilic, right? Just by its very virtue and its very nature. So it has to do with the water. What they argue is that, let's say that this is primarily hydrophobic. I should have done it in a different color. That this is like that middle part is hydrophobic, and so we have this water, which I'm just going to do as W. Well, since it's an aqueous environment, that water has to line up in a very specific order in order to try to avoid it as much as possible. So when the protein folds, it excludes that water, so then the water, its entropy is greatly increasing. So now the water is going to do everything. So that's their argument. That it really isn't a violation of the second law of thermodynamics because of the fact that it all has to do with the water. There are so many water molecules there, and that the water molecules, if the protein didn't fold correctly, would have to be forced into a very specific structure itself. And so it has to do with their definition of system and surroundings, I guess. All right, and so this is just a review of the thermodynamic terms. I would expect you to know these at this point in time. Gibbs free energy is G. It's not the only free energy term that's ever used, but in biochemistry and biology, it's the one that we use. There's enthalpy, which we use the letter H. Gibbs free energy many times is going to be in joules per mole or calories per mole. Same thing with H. And then entropy has another contingent to it because it's also dependent upon temperature. So that's what that K is for Kelvin. And for whatever reason, and maybe you remember this from Gen Chem, a lot of the standard tables put kilojoules for Gibbs and enthalpy, and then just joules for entropy. I don't know why. So make sure that you're always looking at the units. Pay attention to the units. Okay. I'll give you a moment to get caught up. Like I said, this shouldn't be new. We've been discussing entropy, and it's this whole idea of randomness or disorder in the system. Enthalpy, the nice thing about it is since we are isobaric, and for the most part isothermal, it has to do with the heat of the reactions. Enthalpy is a little bit more, it's more complex than just heat, unless you're in an isothermal kind of reactions, isobaric in particular. Okay. And so it has to do with the types of chemical bonds and also the number of reactants and products. And then of course energy. Okay. So when we say something is spontaneous, a spontaneous reaction, what does that really mean? It doesn't require any energy from where? From the outside sources. Does it tell you anything about how quickly it is going to occur? What? Did you say rapidly? Are all spontaneous processes rapid? Not necessarily. So it doesn't tell you, because it depends. You know, you take a nail, they will rust. That's spontaneous, but it may take a long time for it to rust. Right? Okay, that has to do. Those are kinetic interventions then. Okay, in order for something to be spontaneous, how do we know? Based off of these right here. What on this page, tells us whether or not the reaction will be spontaneous or non-spontaneous? G. What must G be in order for it to be spontaneous? Negative. If G is positive, then it's non-spontaneous. If it's negative, it's spontaneous. What does it mean if G is 0? It's at equilibrium. Namaste. Okay, that's what this is all saying. And once again, we're talking about delta G. But once again, just because something is spontaneous doesn't necessarily mean it won't have any enzymatic help. Does that make sense? Because of the fact that it may take a long time, essentially forever. That was in vivo when it's in and so you want it to be negative. The term that's used is called exergonic. If it's positive, it's endergonic. So energy is required. Some type of external help is required for it to take place. Awesome. And we're going to be talking pretty much in every metabolic pathway. A lot of times I'll give you the breakdown for the delta G's. Because delta G, many times, not always, but many times it's also indicative of what step or steps are checkpoints for that metabolic pathway. You'll see what I mean, especially with like glycolysis. That's a good example, and that's coming up next chapter. I think it's next chapter. Okay. This is also just a review from Gen Chem, that they have standard states. For substance, for solid or liquid, you've got to have pure for the standard state. For gas, they use the pressure of 1 atm. For a solution, it's 1 molar, which is 1 mole per liter. And so then, and I would expect you to know this equation, know how to use this equation as well. But they said that delta G is equal to delta G naught, in a little circle, plus RT natural log of the reaction quotient, products of the reactants raised to the power of the stoichiometry, of course. T has to be in Kelvin, and then R is 8.31 joules per mole K. It's also, or it's 0.08206 liters times ATM divided by mole K. Yeah. I would definitely give you the R, what R was. All right. This gets, I'm going to actually work it out so that way you can see, plus it gives, that way I don't go too fast too, is by definition, like what we've been talking about, remember if delta G is equal to 0, you're at equilibrium. And so if you solve for this, you'd have 0 is equal to delta G naught plus RT ln of, I'm just going to say products over reactants, just because I don't want to, but you know this, actually a more correct term for that. Does anyone know what a correct term for that is? What is this right here called? All of this, they call it the reaction quotient, or Q. Which, once again, is just products over reactants to the power. So if we subtract that big Q part, we would have negative RT ln of Q is equal to delta G. And so this Q is given a special name. That Q is the equilibrium constant. So you can just that's the equilibrium constant, KEQ. That's actually how Q and K are related. KEQ is a very, very specific Q. Okay. That's what this is showing you. Is that they just call it? All right. So if you're just looking at, actually, if you look back at the previous one, I'm not gonna go back there, and you saw the standard conditions. What's one of the problems with that in vivo? They usually don't talk about this in Gen Chem or organic. What's one of the problems with the standard conditions in vivo if you use the chemistry standard conditions?
The pressure, atmospheric pressure.
It's usually, especially here in Florida, it really is one. So not usually that's not a problem.
What's the temperature?
Temperature is one. But what's the standard temperature in Gen Chem? Do you remember what it was? I don't think I even put it on there.
Was it 273 Kelvin? That's how you do the conversion.
78. 73.
No, it's 25 degrees Celsius, which is 298. So that's why you guys have 298 Kelvin. But yeah, it's 25 degrees Celsius. What's the problem with that in vivo? What's the problem with that in vivo?
We're 98, but that's not 25 degrees Celsius.
Yes, it's 37 degrees Celsius, which is 310 degrees Kelvin. Okay, but yes. So that's one. That's one. That's the one that usually people can pick up on and remember. That's the easy one. There's at least 3 problems that are wrong for biochemistry. Does anyone know what's another one? And actually, the 2 and 3 are related to the same issue.
pH.
What?
The pH.
pH. That's a big one. What's the problem? And general chemistry
It's
and
not
physics,
constant.
it's 1 molar, which 1 molar would be pH of 0.
Yeah.
That is not the pH. So typically what pH do we use for the standard conditions in biochemistry? Roughly they usually use pH 7, okay, whenever they give you the tables. And then there's another one. And then the third one is the one that people usually don't remember or even don't forget. It's a concentration of something very, very, very particular. If you knew it right now, I'd probably get another 5. What? Magnesium. Concentration of magnesium. So right here. So that's why the problem is if you use the same conditions from Gen Chem for biochemistry and biological systems, we'd have the problem, which one of them is temperature. The second one is pH. Literally, it would be pH 0, and that your stomach would be the closest thing to that. Okay, and so what we do here is we say the standard state is pH 7, and then if magnesium is involved at all, then we consider it 1 millimolar. They're making symbols that say 5, but it's roughly 1 millimolar. Okay, and that's because magnesium. Why is that so important? What is magnesium associated with?
Enzymatic activity.
And there's enzymatic activity. What else is it associated with? It's associated with lots of enzymes, especially those that involve. I mean, first of all, what's so special about magnesium right here in the first place? It's charged, it's 2+.
Water?
Not so, I mean, sometimes it's involved in water, but it's definitely, in vivo, it's always involved with one thing that's not in particular, that we have lots of in our body. So what did someone say?
You said chlorine?
No, not in this instance.
Oxygen.
A very specific type of oxygen.
O2 reactive.
No, it's not elemental oxygen. It's the oxygen that's connected to something else that we've got lots of. What? It can be for antioxidants, but even more so than this. Like if you stretch it out, like I forgot how many meters it would literally. DNA, phosphates. It's phosphates. Like the DNA backbone literally has like magnesium for every so many phosphates. So anytime, and that's just a nice little rule of thumb to have. If you can't remember, if you just like, I know there's there's the cofactors that is around in this one. If a phosphate is involved, anytime you have kinases, 99.99999% of the time they're going to require magnesium. Okay, and seriously, it's like 99.99% of the time. If there's a phosphate there's going to be magnesium, in vivo at least. All right, and so they give it a different symbol. The symbol here is delta G not prime. Little delta G. I don't know. We always call it not. I don't know. Delta G. Not prime is easy to remember. Okay, so this is just for an example. This is the hydrolysis of ATP. Actually, we'll find out when we talk about ATP later on. ATP not only can it hydrolyze to make ADP, but it actually hydrolyzes to make multiple products, and this is just one of them. And so notice it says KEQ prime to let you know it's under biological conditions. And that one does say 25 degrees. So okay, and so something important thing there. But what happens here is whenever we do the hydrolysis of it, KEQ, and I will give you the numbers for all of this kind of stuff. And actually this one, Biochemistry there, using 298, so that's important in this sense. But what you do is you get this delta G. Delta G, once again, is a negative number. That's the important thing. I'm not so much worried about the number itself as in the value, the fact that it's negative. Okay, and so since it's negative, it's going to be spontaneous.
Why isn't water included in the equilibrium constant?
Why isn't it? Does anyone remember? That's the same thing. That's the same. It's true for both Gen Chem, biochemistry, organic, and all that.
Liquids are included.
Liquid. Its concentration is relatively unchanged. It's still going to be 55 molar, 55.5 molar, I think to be exact. The amount of water you had before, that one water molecule taken out of a gazillion,
Oh, okay.
has no change. Same thing with like a pure solid, which we don't really see that typically in our stuff, and Gen Chem you do. Okay. This just to show you this is actually a little summary. I usually, if you remember the stuff about the delta G not prime, and the relation between delta G and K, you can think of this one out too. But K, it has to do with 1. But usually what I always did is I just knew delta G, and if you know that delta G is equal to negative log of K, then you can figure it out that way. Okay. One thing I wanted to point out real quick here is that please note that there is this little part here that they're assuming that you have 1 molar concentration for everything. That's usually not going to be true, right? So then you will have to use the big equation. The one that's delta G is equal to delta G not prime plus RT ln of Q, where Q has all of those concentrations and stuff in it. Okay. All right. Oh, one other thing I wanted to point out. Do not memorize this. This is just to give you an idea. I actually had a student who I did it memory. So did not do well on exams and things like that. She couldn't understand. Like she could tell you page 296 has this reaction on it, but if you move something else around, she couldn't remember. Okay. But this is to show you the relative delta G's, okay, whether or not they're spontaneous or not. But please note these are under standard conditions, and almost always the cell is not going to be under those standard conditions, especially the 1 molar. That's what we mentioned. Okay.
Do we need to memorize this chart?
No.
Okay.
I had just said don't memorize this chart.
Sorry.
It's okay. All right. But like what I could say is, for example, I could tell you something like, give you this information here and ask you if it's spontaneous or non-spontaneous. Okay. And you can see that they are not all created equal. Like some of these are much larger. In fact, what we'll find out is ATP is not the best at giving you energy in vivo even. And so we'll talk about the reason why that's important later on. Okay.
Does the more negative value of delta G have anything to do with rate or?
No, not necessarily. Okay. So by their very virtue, I don't know how much you remember from either thermodynamics or how much enzymology you know. Capital K, the rate is based off little k, how fast it is going based off little k. By its very nature, capital K and little k are related to each other, but you have to know more information. So if you know 2 of the 3, then you can figure out the third. So, and it also depends on which direction you're talking about. Once again, typically, if I just gave you a number, then no, not necessarily. It won't tell you how fast it is. It's going to let you know it's going to go. Okay. So this is the Q. I've kind of argued in that way. You don't know why it didn't become so pixelated. But delta G is equal to delta G naught prime plus RT natural log of the reactants. Reactants. Products over reactants. Products over reactants. Raised to whatever power is from the coefficient. This is the best one to know. Because even if you have problems remembering one for equilibrium constant, if you know this one, you can solve for the equilibrium constant. Because remember, equilibrium constant is this. Literally, it means this at equilibrium. So that's why you're going to know one and only one. That's the one to know. All right. This is also a review, but I'm going to give you a moment to think about it real quick. Or to write it down, first of all, and then to try to say, what does that mean? Some examples. Okay, there you go. This is just an example. I'm trying to do it in my head. This is an example using for delta G. Here, I'll try to do one for K. In this color. Okay. I gotta try to think what it is. Oh wait. Oh, just a second. Let me. Okay, there we go. And this is always true for the K's. Just because I didn't put a prime next to it, that's why I'm saying it doesn't matter that I forgot to put the prime next to all the K's. So, one thing to remember is standard free energies, the delta G's are additive, and the K's are multiplicative. So, knowing that in the red, if A plus B goes to C, the delta G is negative 10, then E plus F goes to C plus D, and the delta G is negative 25. So then, knowing all this, what is A plus B plus D going to make E plus F? What's the delta G? Pardon? Okay, and so I deliberately picked this one because what we have to do is you have to learn how to manipulate each of these. This is correct, going in the correct direction, so we don't do anything to change that number. So we're going to have negative 10. But what do we have to do to the second one? In order for this to be true, D has to be on the reactant side. So we have to flip this equation over, and when you flip it, you change the sign. So even though it's additive, you're going to be, whoops, that's not what I wanted to do. It's going to be plus, oh, don't do that to me, plus 25. So it's going to be positive 15. Then I could ask, and that would be kilograms per mole. I could ask you, is that spontaneous or non-spontaneous? In this instance, in this example, it would be non-spontaneous, it's a positive number. So in the second example, in the blue, with the K's, what's going to be the answer for it? A goes to B plus C, the K is equal to 1/2. C goes to D plus E, the K is equal to 5. So if A goes to B plus D plus E, what is the K going to be equal to? 5/2. Because you just multiply the two. What would have happened if, and I didn't do this one, if it was one like, if we did the exact same here, let's do the exact same thing, but that with K on this side. So I'll give K value, well, this would be different. Let's say instead of delta G, each of these were K's. So let's say K was negative 10 and K was negative 25. What would be the K overall? We'd have negative 10. Well, we can't have negative 10. Let's say 10 and 25, okay? So we would have 10 and 25. So we're going to have K would be equal to 10 times, what is this one right here? What do we do with this? You have to take 1 over it. This is 1 over 25. So then it's 10 25ths, which would be 2/5. Okay. Sorry, I ran out of room. But yeah, that's the one thing with the K's. Is you have to realize you don't just take the opposite sign, you actually do the reciprocals for it. Whereas the G, if you're flipping around, you just change the sign. Negative, positive, positive, or negative. Okay. And that's all this first part I'm going to cover. Are there any questions over this?